One of the handy pieces of information that we can get from a balanced chemical equation is the mole ratio between two of the species that appear in the reaction. We're going to talk about that briefly in this video. Our learning goal is to use this to predict the amount of product that's generated by a particular reaction. So let's step back and look at the balanced chemical equation again, and I want to talk a little bit about what it means. So here's an equation that we balanced in an earlier video. 2NO reacting with oxygen molecules to make 2NO2. Now, one of the ways that we can interpret this is to say, well, that's 2 molecules of NO reacts with 1 molecule of O2, and it generates 2 molecules of NO2. That would be perfectly correct, and that is one way you can interpret this. However, we could also take those 3 quantities and multiply each of them by 1 mole. Okay, when we multiply a molecule by a mole, now we're going to have 6 times 10 to the 23rd of them. And now, instead of molecules, we're talking about moles. So now this equation would imply I'm talking about 2 moles of NO is reacting with 1 mole of oxygen diatomic molecules to produce 2 moles of NO2. This is another perfectly legitimate way of interpreting that balanced chemical equation, and it's going to be more useful for us in some ways because a mole is something we can measure in the lab, whereas individual molecules are very difficult to measure. Now we can also make some alternative interpretations of this. We could say that 1 mole of O2 reacts with 2 moles of NO, which implies that the mole ratio of diatomic oxygen to NO is 1 to 2. Similarly, we could say 1 mole of O2 produces 2 moles of NO2 in this reaction. So that implies a mole ratio of O2 to NO2 of 1 to 2. Now notice that these mole ratios that I've drawn out are just the coefficients that appear in the balanced chemical equation. So if you have a balanced equation, if you know how to read it, you don't have to think very hard to get a mole ratio. You just need to find the ratio of one coefficient to the other. So let's see how this might work in terms of converting moles to physical quantities. So once again, we may use our chart, although we probably won't need it for this particular exercise. But once again, we have our reaction, 2NO plus O2 goes to 2NO2. And now I'm going to use the molar interpretation for this. Now in this case, what I want to do is I want to convert these into some amount of grams that I might measure in a laboratory. So I'm going to start with moles, I'm going to go to grams. In order to get there, I'm going to have to multiply by the formula weight for each of these compounds. So as I go down, now to multiply by the 3 formula weights, I'm going to end up with 30.01 times 2 moles gives me 60.02 grams of NO. I've got 32 grams per molecule of O2, so that's going to end up being 32 grams of O2. And 2 moles of NO2 times 46.01 grams would give me 92 grams of NO2. So in the end, what I have is an equation that tells me that 60.02 grams of NO combine with 32 grams of oxygen to produce 92.02 grams of NO2. So I've basically taken my balanced chemical equation, and by using the formula weights, I've converted this now into a statement about actual masses that would combine for this reaction. This is the very heart of stoichiometry, which is the study of how to quantify the results of chemical reactions. One last thing I want to mention, you'll notice that 60.02 plus 32 is equal to 92.02. So this very nicely illustrates how the balanced chemical equation upholds the law of conservation of mass.